Welcome to our video on problem solving. We're going to look at the use, solve, and explain method, and then we're also going to look at a separate method that I've come up with. So this is a typical method that a lot of textbooks present. The U.S.E. use stands for understand, solve, and explain method for tackling basically word problems and things like that. And it can actually be, expanded to just tackling everyday problems if you're trying to figure something out in life. So the first thing you want to do, understand the problem. And by understanding the problem, that means you want to think about what the problem is asking you to do, draw a picture or diagram if you can. Oftentimes just a simple little stick diagram of something will help you kind of get focused on what the question is all about. Ask yourself what the solution should look like. Basically, try to make sure that you're identifying the question and identifying what it is you're trying to solve for. And then try to map a path, either mentally or in writing, that will lead you to the solution, right? Like, how are you going to get from point A to point B? And then continually revisit that understanding of the problem as you work through it. Step two, simple. The S is just for solve the problem. You might say, well, yeah, sure, simple to you, but how do we actually do it? Well, the nice thing about solving these things is if you generalize these steps, it really just matters. It only comes down to kind of using different tools for different problems, but you're still going to use kind of the same overall recipe. The first thing you want to do is obtain any needed information or data. So, i.e., look through the question if you're dealing with a word problem and pull out all the important bits and pieces. If it's a real world thing, then maybe you have to do some research, maybe you have to look something up, maybe you have to ask some experts or whatever, but you want to get all the information and data you can on this particular problem. For multi-step problems, you want to be sure and keep yourself organized, keep everything neatly written, record of your work. So if a problem arises, you can always kind of look backwards and figure out where you messed up. It's easier to kind of check your work and back up and fix something and then go forward rather than having to start all over again if you stay organized. And on that same vein, you should be double checking your work and double checking your steps as you go to avoid making an error and carrying it through, to the next step and possibly all the way to the end of your solution. And then you always want to be reevaluating your plan as you go. After you do a couple steps, ask yourself, am I really on the right path? Does this feel right? And then try something else if you have to. Lastly, you want to explain your result. You want to make sure that the result makes sense. In a context of solving a problem, you would plug your solution back in and make sure that it checks, that you get the correct answer, that it works. But also sometimes you need to make sure that the result makes sense in the context of the question. If you get, for instance, if you're trying to solve for a volume and you get a negative answer, you're like, well, I can't have a negative volume, so I must have messed up somewhere. Recheck your calculations one more time, and even better if you can, find somebody else to check your work for you, right? So this goes back to if you're doing this in the real world, you get a coworker or somebody to look over your results and look over your work, and usually a fresh set of eyes can find something easier than you can. Identify and understand any potential sources of uncertainty in your result. If you made some assumptions, were they reasonable? Write your solution clearly and concisely using complete sentences to make sure the context and meanings are clear, i.e., you want to make sure that what you've done matters, right? I mean, if you get a result, that's great, but if nobody else can figure out what that result is because you can't clearly communicate that to others, then it makes no sense, right? Like, who cares if you've got a result if nobody else can understand it? Okay, so here is kind of my version of the four-step. Um, I know there's just three, but mine is four. And this is more geared towards just math, right? Trying to problem solve a math question. And you'll see that there's a lot of correlation to the general three-step problem. So if you're faced with a word problem, right, that you're trying to solve, The first thing you want to do is read the question all the way through. And all you want to do on that first read through is these three simple things. You want to understand the overall theme of the question, right? Is it talking about objects moving? Then you know that, okay, this is going to be like a distance equals rate times time question. Or is it describing some sort of geometric figure? And then you're thinking, okay, I got to start thinking about geometry and all the formulas for volume or area or whatever I'm dealing with, right? So just come, is it talking about money? Is it talking about exponential growth, right? Just find the theme. Is it a quadratic equation? So I know that I'm dealing with parabolas and those kind of things. So you're just going to identify the general theme of the question. You want to identify the question itself. Somewhere in that word problem, it's going to ask you to find something, right? i.e., what do you need to solve for? And that's what you label as your unknown. And please don't get in the habit of always labeling your unknown as X. It doesn't always have to be X. If you're trying to find the cost of something, then label it C. If you're trying to find the area of something, label it A, right? You can label it anything you want. You might as well label it something that makes sense. And then you want to draw some sort of simple picture or diagram, or maybe create a table depending on the type of question it is. Depending on the theme, one of these three things will help: a picture, a diagram, or a table. Usually a table is used for more complex multi-step questions where we have to keep our information organized. For simpler questions, we can draw a simple picture or a simple diagram. And by a simple picture, it could even be something like talking about, oh, a train is going east at a certain amount of speed, and another train's going west at a certain amount of speed, and how long until they meet in the middle. We'll just draw a straight line. And then you can label, the left side of the line with the train that's moving to the east, and label the right-hand side of the line with the train that's moving to the west, right? So you can keep everything kind of visually in perspective. Then you go back and reread the question in bite-sized pieces. And by bite-sized pieces, I mean just take each little phrase at a time. And you want to translate each little English phrase into math and write down all the info that it gives you. So, a train traveling east at 60 miles per hour. Then on your picture, you put, a little arrow pointing to the east, and you put 60 miles per hour. And the other train leaves 2 hours later, and you write over there, and you did it right. So you're labeling all the parts of your picture. You're putting things in your table. You're labeling your diagram, whatever that is, right? You're taking all those little bits and pieces, and you're translating them into math, and you're writing down all the information because you want to get to a point where you don't have to go back and read the question again. It's everything you need is just right there on your paper. And the last thing you want to try and do is find that hidden equation. Somewhere in all of that information, they talk about something equaling something else. And that's your equation, right? Because you have to solve for something. In order to solve for something, there has to be an equation. So that's the hardest part usually, is finding that hidden equation. But when you write down all the bits and pieces, and you draw a picture and start labeling stuff, it makes it easier to find that hidden equation. Step 4 is just solve the darn thing, right? Now that you found that hidden equation, go ahead and solve it using the appropriate techniques, right? If it's quadratic, maybe use the quadratic formula. Maybe you're completing the square. Maybe you're just factoring it by the guess and check rule or the AC method. If it's a linear equation, and you're using simple techniques of solving a linear equation, right? It all depends on what it is, how you solve it. And the last thing you want to do is check that answer, make sure it's correct, and make sure that it makes sense. As I said before, in the context of the question, does it make sense, right? If we're talking about distances and areas and volumes, oftentimes, especially with quadratics, you'll get two answers. You get a positive and a negative answer, but the negative answer doesn't make sense because you can't have negative area or negative distance. So you throw that away and go, this is my only answer, the positive one. Okay, so that's how we're going to tackle word problems. Okay, what about units? If we have to deal with different units, well, a unit is basically just a description of the type of quantity that we have, and unit analysis is the process of working with units to help solve problems. So oftentimes you'll have problems where they'll talk about, acres or hectares or square meters or square kilometers, right? If you're in the metric part of the world. Those are all just units of measure. Dollars, right? That's a unit of measure. And whatever kind of dollar it is, U.S. dollar, Canadian dollar, or the British pound, right? Those are all just units of measure. And you just need to understand that those units come into play when we're trying to deal with these questions. So for instance, if you're buying 30 acres of farmland at $12,000 per acre, what's the total cost? Well, you understand that it's asking you to find total cost, so you have to come up with an equation for cost, right? And very simply, you're just going to go, oh, well, cost is just going to equal area times price. So it's going to be 30 acres times 12,000 per acre. You'll notice that per means a fraction. Anytime you see per, right, dollars per acre means dollars over acre. And then when you multiply these things, the acres cancel, right? You've got this is like acre over 1. So the acre and acres cancel, and you get 30 times $12,000, and you're just left with $360,000, right? The acres go away in that question. How about show operations in units clearly to answer the question, what is the total distance traveled when you run 7 laps around a 400-meter track? Well, again, it's the idea of what's total distance. Well, total distance is just how far I ran, right? Okay, well, I did 7 laps, but I don't know, well, a lap is 400 meters. So it's going to be 7 laps times 400 meters per lap. See, that per again puts it in the bottom of a fraction. The laps cancel, and you're left with 2,800 meters. So this brings us to this idea of being able to translate math with certain words. Per is always going to mean division, right? So miles per hour is always miles over hour, right? Of or hyphen is multiplication. So kilowatt hours, right, is kilowatts times hours. Square obviously means raising to the second power. So feet times feet is feet squared. We read that as square feet or feet squared. We usually say square feet like we say cubic feet, but some people say feet squared and feet cubed, and that's just when it's the third power. A conversion factor is simply just a true equation, right? You can see these all have equals in them, and it's just something that equates one unit of measure to another unit of measure, like 12 inches in a foot, 24 hours in a day. Or you could say 12 inches divided by 1 foot equals 1, right? 24 hours divided by 1 day equals 1, because of the same thing. And of course, if 12 inches over 1 foot equals 1, then 1 foot over 12 inches also equals 1. So those are conversion factors. They help you convert from one unit of measure to the other. So we can convert a distance of 9 feet into inches by doing 9 feet times the 12 feet per 1 foot, 12 inches per 1 foot thing. The feet cancel, and we get 108 inches. So let's look at this. 94 days without a single homework assignment or test. 94 days, that's so many hours, that's so many minutes, that's so many seconds, right? Of course, my math brain waits until now to show up, right? Funny. But how did they get that? Well, it's just through a bunch of conversions, right? You go from days to hours, hours to minutes, minutes to seconds, and then you're just multiplying all of the numbers, because this one's technically over 1. So when you multiply fractions, it's tops, right? And then that's where you get that big, huge number. If we have to convert things that are to powers, like square feet or cubic feet, just realize that the conversion factor gets squared or cubed as well, right? So if 1 yard equals 3 feet, then 1 square yard equals 3 feet times 3 feet equals 9 square feet. And if we want to do a cubic yard, then it would be 3 feet times 3 feet times 3 feet, and you'd have 27 cubic feet in 1 cubic yard. So, for instance, how many cubic yards of soil are needed to fill a planter that is 20 feet long by 3 feet wide by 4 feet tall? Well, you figure out the volume of that planter, and you go 20 times 3 times 4, and you get 240 cubic feet. And then we know that 1 yard is 3 feet, so 1 cubic yard, right, as we said, we cube the whole thing, is 27 cubic feet. So all we have to do is take this number, multiply it by its conversion factor, which is cubic yard over feet, 27 of them. The cubic feet go away. You basically take 240 and divide it by 27, you get a little less than 9 cubic yards. So then you can call up the landscape, supply place and tell them you need 9 cubic yards of soil, and you'll be able to fill up your planter. So this brings up the conversion line technique. So far, all of these examples, we've just been writing them out. But a nice thing to keep all of these things organized is a simple technique that I call the conversion line, for lack of a fancier word. And all it is taking something like the previous one, like this, and more formalizing it. So when we have a question like this, we can think of, what's happening here? Well, it really is as if we're working with one big, huge fraction, right? This is just one line. Sorry, sometimes my pen does weird things. This is just one line here. And we'd put this 94 days on top of the line, and it'd just be over 1. And then you can think of these as just being compartments. And each compartment always has to equal 1. Each of these things has to be a fraction equal to 1, because you're going to multiply 94 days times 1. So when you get to the end, these two things are still equivalent because you've just multiplied them by 1. But what you've done is you've multiplied them by weird versions of 1 so that your units of measure will change. So let's say we wanted to do, let's figure out, we can even do this with mixed stuff. Let's step it up a notch. Let's say we're going to take something that travels at 200 feet per second, and we want to convert it to miles per hour. Okay, well, remember, per second, puts it over. So that's why we know that's per second. So we're going to multiply it by a bunch of things to get it into miles per hour. Well, the first thing you might think of is, okay, I'm going to change feet to miles. And I know there's 5,280 feet in 1 mile. Now, how do I know the mile goes on top and the feet goes on the bottom? Well, I want to get rid of feet. And since there's feet here, I need feet on the bottom for those to cancel. Now I'm in miles per second. I would do 200, and I would divide this by 5,280, and that would give me my answer in miles per second. But I don't want miles per second. I want miles per hour. So then I go, okay, well, there are 60 seconds in 1 minute. Now the seconds are going to cancel, and we're going to be in miles per minute. And that's close, right? We don't want minutes, so we go 60 minutes in 1 hour. And again, those will cancel. And when we're left, we're going to have miles over hour, and that's going to be our answer, miles per hour. So if you take out your calculator and do 200 times 60 times 60 and divide by 5,280, you get the answer in miles per hour. I don't know off the top of my head. I think it's like 160 or something like that, but you guys can do the math. You get the idea. That's how the conversion line can convert anything to anything, right? It can convert just something as simple as cubic feet to cubic yards, or what we call a compound units, where we have feet per second, right? So it's a great technique to keep everything organized, and it helps you understand which measurement goes on which side of the line, so to speak. Now, this one I don't want to talk about because who's ever heard of furlongs, right? So, but you guys can look at this on your own. We've already done enough of these. Instead, let's get into the metric system. We're like one of the only major, we as being the United States, one of the only major countries that still is not on the metric system. So it's a good idea to learn it because everybody else is using it. So you want to know what it means. The meter is for length, right? Kilogram for mass, second for time, just like us, and then liter for volume. So they've all got common prefixes that all come from Greek. So all of these things are basically based on Greek letters. Centi means 100 in Greek, so that's why we have cents, right? 100 cents in a dollar, and that's why a century is 100 years. So all of these things come from those ideas. A decimal, right, is each tenth is a decimal, so that's where deci is 1/10. So we can convert 2,759 centimeters to meters very easily because we know there's 100 centimeters in a meter. So you're basically just dividing by 100, which really just means you move the decimal place 2 spots to the left. That's the beauty of the metric system, is to convert back and forth is really just a matter of moving the decimal places. Now, if you want to convert from the US to metric, then you have to have conversions like 1 mile equals 1.6093 kilometers. The one official conversion that we have is 2.54 centimeters equals 1 inch, and then everything is built off of that. So actually, this 1.6093 just comes from starting with 2.54 centimeters per inch and then building those both up, right? Taking centimeters up to kilometers and taking inches up to miles, and then you get that conversion. Then there's also the Fahrenheit scale versus the Celsius scale, right? Again, we're one of the only countries left that does Fahrenheit. Everybody else does Celsius because Fahrenheit, for some strange reason, is defined that water freezes at 32 degrees and boils at 212, whereas the Celsius scale has been augmented so that water freezes at 0 and boils at 100. It kind of makes a lot more sense to have it on a scale of 0 to 100. So that's why the rest of the world uses the Celsius scale. There's also the Kelvin scale, which is really only used by scientists. And the reason why they have the Kelvin scale is it's for getting super, super low numbers when they're doing experiments where they're trying to reach absolute zero, which has never been reached and in theory can't be reached. But 0 degrees Kelvin, absolute zero, is supposed to be negative 273.15 degrees Celsius or almost negative 460 degrees Fahrenheit. Scientists have gotten really, really close, but they've never actually gotten it that cold. So here are the basic conversions to go back and forth between Celsius and Fahrenheit. All right, so here's your formula. Fahrenheit is just 1.8 times Celsius plus 32. If you're ever traveling in a country that has Celsius degrees and you want to kind of figure out what that is in Fahrenheit, a really quick, easy approximation is just double the Celsius and then add 30, right? So instead of multiplying by 1.8, you double it, which is a little bit too big. So instead of adding 32, you add 30. And those two things offset each other enough that your answer is going to be close enough that you at least know what to wear, right? You're at least going to know if it's going to be a really hot day or a really cold day when they tell you it's going to be 25 degrees Celsius tomorrow. You're like, what the heck is 25 degrees? Well, I double it, which is 50. I add 30, which is 80. And you go, oh, it's roughly 80 degrees Fahrenheit. I'm going to wear shorts. It's that kind of thing. So here's another example of how to convert it the right way. Again, I don't want to spend a lot of time on that because you guys can just pause the video and go through it. And same thing with the money, right? US dollars and euros. It all depends on what the conversion rate is, which of course, this is what it was in 2013, but it's completely changed as of today. So if you wanted to figure out how much fuel actually costs, just know that you would put the cost down and then you would have to convert the cost to US dollars, but then you'd also have to convert liters to gallons, and then you would get the price per gallon. And then when you're over in Europe, you can go, holy moly, this gas is expensive. All right, that's it for this video.